Good evening, Doctor. We are from Group 10. We would like to present about hybrid problem of linear and non-linear. Our group members are Nanna, Richenda, and Mei.
My name is Nanna Maisara binti Masri with number matrix of BS2211038. We'll be presenting about Gaussian elimination of linear system and bisection for nonlinear method. In Gaussian elimination, it has a direct method that solves the system in two clear phases. First is forward elimination. In this phase, we use row operations to eliminate variables below the main diagonal, transforming our matrix into an upward triangular form. Second is backward substitutions. Once we have the triangle shape, we solve for the variables in reverse order, starting from the bottom equation and working our way up. So, I started with the augmented matrix. First, I used row 1 as my pivot to eliminate the entries in the first column. I multiply the row 1 by 0.5 to zero out the second row, and I multiply the row 1 by 0.75 to zero out the third row. Next, I move to the second column. I use the new row 2 to eliminate the entry in row 3. This gave me the final upper triangular matrix you see at the bottom with zeros in the lower corner. For the backward substitution, first, I solved the last row for y3, which gave me exactly 8.104. Next, I substitute the value I got, which is 8.104, into the second row to solve for y2, which we get 6.913. Finally, I substitute both values into the first row to find y1, which came out to be negative 0.600. So, the final solution vector for this system is y1 equal to negative 0.60, y2 equals to 6.91, and y3 is equal to 8.10. Next is algorithm demonstration. First, for the first one is forward elimination. The goal here is to transform the augmented matrix into an upper triangular matrix. The algorithm iterates through the diagonal elements, using them as pivots. For each pivot, it calculates a multiplier to eliminate or zero out all the entries in the column directly below it. For phase 2 is backward substitution. Once we have the triangular form, we solve for the unknowns in reverse order. We calculate the last variable y3 directly. Then, we loop backwards, substituting the known values into the previous equations to solve for the remaining variables, which is y2 and y1. Next is theoretical justification. So why Gaussian elimination? Because it is the direct method, which computes the exact solution in a finite number of steps. Unlike iterative methods, it doesn't require an initial guess or convergence criteria. For a small system like this 3x3 matrix, it is the most robust and standard choice. Second is stability and error control. While the method is theoretically exact, a key potential issue is the run of error. In computers, dividing by a very small pivot number can cause errors to accumulate, leading to an inaccurate answer. However, in this specific problem, our pivots 4 and 8.5 were relatively large and well scaled. This ensures that the calculation remains stable without requiring advanced pivoting strategies. Next is critical discussion. Firstly is computational cost. This is a direct method, which means it finds the theoretically exact solution in a finite number of steps. Unlike iterative methods, it doesn't need an initial guess, making it very efficient for a small system like this 3x3 matrix. Next is major pitfall. Because computers use finite precisions, dividing by a very small number can lead to significant errors that swamp the solution. In large-scale engineering problems, this easily requires a strategy called partial pivoting to fix. Next, for the nonlinear method, I implemented the bisection method. So we have to find the initial interval AB, where the function signs are opposite. So after some calculation, I got G0 equal to positive and G1 was negative. Now, looking at the calculation, in iteration 1, my midpoint was 0.5, so the function value was positive. So we have to replace a since a is positive. My new interval was 0.51. So I calculated the midpoint, C, and my new midpoint becomes 0.75. This time, when I plug 0.75 into the function, the result value was negative 0.27. Since this is negative, it replaced my upper bound b, so my upper limit moved down to 0.75. For iteration 3, I calculated the new midpoint between 0.5 and 0.75, which is 0.625. I evaluated the function at 0.625 and the result was negative 0.089. Because it is negative, I had to replace the upper bound b again, so my interval narrowed down to 0.5, 0.625. For iteration 4, the midpoint of this new interval is 0.5625. The function value here was positive 0.007. Since it is positive, this time I updated the lower bound a, so the interval became 0.5625, 0.625. By iteration 5, the midpoint was 0.5938 and the interval was small enough to conclude the approximate root is 0.5781. And the interval was small enough to conclude the approximate root is 0.5781. Next, we move on to algorithm demonstration. The algorithm relies on the intermediate value theorem. We start with an initial interval AB where the function signs are opposite, meaning GA and GB have different signs. This guarantees a root exists between them. Inside the loop, we calculate the midpoint C. We then evaluate the function at this midpoint. And for the decision step, if GA and GC have opposite signs, we know the root lies in the left half, so we discard the right side by moving B to C. Otherwise, the root lies in the right half, and we move A to C. We repeat this process until the interval size is smaller than our error tolerance, giving us a precise approximation. This is the step-by-step data of calculation to find the approximate root. Now, let's visualize the solution using the graphical output. Here, I have plotted the function gx e negative x minus x over the interval from x equal to 0 to x equal to 1. The blue curve represents our function, while the horizontal axis represents y equal to 0. As you can see, the curve starts at y negative 1 when x is 0 and crosses the x-axis as it descends, ending at approximately negative 0.3 when x is 1. The intersections point, the point where the curve intersects the x-axis, is our root. Visually, we can confirm that this intersection happens exactly between 0.5 and 0.6, which perfectly matches my calculated result of 0.5781. This graphical evidence validates the accuracy of the bisection method. Next is theoretical justification. So why bisection method? The primary reason I chose the bisection method is its guaranteed convergence. This method relies on the intermediate value theorem. Since our function is continuous and we identified it as a sign change between x equal to 0 and x equal to 1, which is 1 is positive and 1 is negative, the method guarantees we will find the root. Unlike open method like Newton-Raphson, bisection is global, which means it will never diverge or crash as long as the root is bracket. Next is convergence and error. The trade-off for this stability is speed. The bisection method has linear convergence. In every iteration, we simply cut the interval in half. This means the error is reduced by a factor of 0.5 each time. While this is low compared to Newton's method, which is quadratic, it is highly predictable. For error control, Finally, regarding our error control, the bisection is unique because we can calculate exactly how many iterations are needed to reach a specific tolerance before we even start. The error is strictly bound by the width of our interval b minus a, so we stop the algorithm once the width falls below our tolerance level, ensuring the answer is accurate. Next is critical discussion. For the convergence speed, it has linear convergence, which is relatively slow. The error is reduced by a factor of only 0.5 per iteration. For global stability, it is unconditionally stable. If the root is bracket, the method never diverges. This makes it safer than the Newton-Raphson, which can fail if the initial guess is poor or if gx equal to 0. For computational cost, it requires more iterations to reach a high precision compared to other methods. It is computationally cheap per step, but it does not require calculation the derivative gx.
My name is Richenda and I'll present the Gauss-Seidel method for linear equations and Newton-Raphson for nonlinear equations. These are the algorithm for Gauss-Seidel method. This algorithm iteratively updates each variable using latest available values and stop when the relative error is below a specific tolerance, producing the solutions to the linear system. For linear system, we are given three equations, equations 1, equation 2, and also equations 3. We are going to rearrange each equations to solve for one variable at a time. So these three boxes below shows the rearrange of the equations 1, equations 2, and also equations 3. Steps 2, we start with the initial guess of 0 and we track progress using the absolute relative approximate errors using these equations number 4. For iteration 1, since all the initial guesses are 0, we are going to substitute it into the equations and then calculate the absolute relative approximation error for all three equations. So the answer that we get from y1 are going to be substituted into this equation 2, similar to the equations 3. We ran into many iterations. Here's a snapshot of how the values evolve. This is iterations 2. By iterations 3, you can see y1 is very small, causing a spike in error that's normal early on, but y2 and y3 errors are already below 10%. Therefore, we need to continue iterations until it converges. By iteration 8, look at the errors, all are below 1.3, with y2 and y3 under 0.1, which means we are getting close to the answer. By iteration 10, errors for y2 and y3 are tiny, which less than 0.01, so our final solution is equals to y1 negative 0.5994, y2 6.9128, and y3 8.1040. So the Gauss-Seidel has been successfully converged. So these are the iterations table and convergence plots that we get from the answer. The error graph shows a rapid decrease after few iterations, confirming convergence. Next, we apply the Newton-Raphson method to the nonlinear equations, which is the equations 1, and then we find the derivative of the equations 1, and then we get equations 2. For iteration 1, we set initial guess of 0.5 and substitute it into each equations 1 and also equations 2. Then we apply the Newton-Raphson formula using these equations 5 to find the answer and calculate the relative error. Before I present further, we are going to look at the algorithm of the Newton-Raphson. The idea is simple. We start with the guess, use the function and its derivative to get a better guess, and repeat until we are close enough. So these are the formulas, and we stop when the relative error is small. After only 3 iterations, the solutions converges to 0.56713. The minus in the denominators make it a plus, showing that we are close enough to the answer. The convergence plot shows that the solution stabilizes very quickly. This happened because Newton-Raphson has quadratic convergence, meaning the error decreased very fast. This method is appropriate because the equation is differentiable and the derivative is non-zero near to the root. To summarize the Gauss-Seidel method, it's especially useful for solving system of linear equations, especially when the coefficients metric is diagonally dominant, which guarantee convergence. The method shows linear convergence, meaning it steadily approaches the solutions with each iterations. We monitor progress using relative approximate error, stopping when the error falls below a set tolerance, and then it is stable for diagonal dominant system and computationally efficient per iterations, making it good for large system. But for the pitfalls, it may diverge if the matrix isn't diagonally dominant. It can be slow for poorly conditioned problems, and convergence can be depends on how you order the equations. As for Newton-Raphson method, this method is perfect for non-linear equations that are differentiable. One of its strongest advantage is its quadratic convergence near the root, which means error shrinks very quickly. We control the accuracy by tracking the relative approximate error between iterations, stopping once it's below our tolerance. It's stable when the initial guess is close to the true root and despite requiring both the functions and derivative to be evaluated. It's highly efficient because so few iterations are needed. But for its pitfalls, Newton-Raphson needs a good starting guess. It can fail if the derivative is 0, and sometimes it may converge to the wrong roots.
Next, I am Hao Yimei, who will be presenting as student C with LU decomposition as linear systems and secant as nonlinear method. Based on the linear system components, there are three equations. First, we write it down in matrix form, and next we write it down A equals to LU as the LU decomposition matrix. First, to find the matrix U, we apply a forward eliminations, which is row by row eliminations, onto the matrix A, which is the coefficients matrix. At last, we will get a downward triangles zeros, which is the matrix form of U. Next, to find L, we use Lij equals to minus Mij, which the Mij is the coefficients from the previous forward eliminations when row by row eliminations. And next, we will get the L matrix in the below. Now we have L matrix equations and U matrix equations. So first we use L matrix equations to find the Z from Lz equals to B to solve for Z1, Z2 and Z3. Now we can solve the linear system with U matrix and Z matrix by solving for Y3, Y2 and Y1 in orderly. In algorithm, the input is the square matrix A, which is a coefficients matrix, and vector B is the right hand side matrix, and the output is the solution vector Y, which is the unknown matrix, and decomposition matrix LUP. And first we initialize NULP as the values need to be initialized, and next we use the for loop for partial pivoting and elimination. Forward substitution is to find the Z matrix, and the backward substitution is to find the unknown matrix, which is the Y1, Y2 and Y3. At last, the algorithm return YLUP, so we get the output. LU decomposition is appropriate here because the matrix is square and non-singular, which make it efficient for repeated solves with different right-hand sides. It converges stable for non-singular matrix when using partial pivoting and provide an exact solution in exact arithmetic. An error can be monitored by check the residual norm and the condition number of the matrix. In nonlinear system, we use secant method here by using initial guess with x0 equals to 0 and x1 equals to 1 for first iterations. Next, we proceed with second iteration and third iterations as the approximate root is not converging. At fourth iteration and fifth iterations, as the approximate root shows converging already, so we can stop iterations here at n equals to 4 and n equals to 5. In algorithm, the input is gx, initial guess, and tolerance and max iterations. And output is the root approximations and iteration history. First, we initialize the number of iterations and initial guess and the secant formula. And we use for loop for each iterations. And in each iterations, we check the convergence and we update values for next iterations. After that, we return the latest root approximations and iterations. In the graph secant method functions and iteration steps, you can see that the exact root is 0.567143, and converge to root graph, we can see that the approximate root against the iteration number, which is the 0.567143 after 6 iteration time, and the error also converge after 6 iteration times. and also for the function value at each iterations and the step size reduction. The second method is suitable here because the function is smooth and does not require derivative calculation, which is simplifying the implementations, and converges superlinearly with an order of about 1.618, which accelerating as it nears the root with only 2 initial guess need. Error can be naturally monitored using the iteration difference and the function value to ensure the accuracy. In aspect of computational efficiency, LU decomposition has an initial higher cost but becomes efficient for repeated solves, while the second method requires minimal memory and only one function's evaluations per iterations, which by avoiding the derivative computation. In potential P4, while LU decomposition requires pivoting to avoid failure from zero diagonals, while the second method can diverge with poor initial guess or near equal function values often need the fallback safeguards. And that's all from us. Thank you.